The ABC of the Universe. The third talk in this BBC series is called The Milky Way and is given by Dr Roderick Willstrop, an astronomer who works at the Cambridge Optical Observatory.
Take a look at the sky on a clear night, choosing a night when the moon is not shining. You will see stars in all directions, but you won't see the same number in all parts of the sky. The most striking feature is that they are concentrated towards what we call the Milky Way. To the naked eye, this is a continuous band of pale light, circling around the whole sky and heavily sprinkled with stars. Some bits of it are relatively wide and bright, as in the southern constellation Sagittarius, and other parts are faint and narrow. This band is a side view of our own galaxy, sometimes called the galaxy, although it's really only one of millions. But although it's so clearly visible to the naked eye, we need a telescope to tell us more about it. When we look at the Milky Way with a telescope, we find that our pale band is really composed of faint stars, each one by itself too faint to be seen by the naked eye. Besides these scattered stars, there are others arranged in clusters. Some clusters, with a few dozen to a few hundred stars, are called galactic clusters, because most of them are found in or near the Milky Way. Others have tens or hundreds of thousands of stars. These latter are called globular clusters from their appearance. They are so compact that we need a fair-sized telescope to resolve their individual stars. Then there are some patches in the Milky Way which can't be resolved into stars at all, and we call these nebulae. Some of these are bright clouds of dust and gas, made to shine by neighbouring hot stars, and we can see these with a telescope or photograph them. Other nebulae are dark, but we can tell they are there because they cut off the light of the faint stars beyond. These, then, are the constituents of our galaxy, together with a great deal of space. But we want to know where they are, as well as what they are. William Herschel was the first astronomer to try to find out how the stars were distributed in the galaxy. He could not measure the distances of any of them, but instead he counted all the stars he could see with one of his telescopes when it was pointed at various parts of the Milky Way and in other directions. He made a reasonable assumption that the galaxy extends furthest in the directions in which he could see most stars, and concluded that the stars were arranged in a flat disk, with the Earth and the Sun near the centre. Broadly speaking, Herschel was right, but in some important details he was mistaken. We now know that the galaxy is much larger than he supposed, and that the Sun is very far from the centre, and we've been able to correct Herschel by measuring how far away from us the stars are. We can measure the distance of a nearby star in just the same way as a surveyor measures the distance of an inaccessible mountain peak. He measures its change in direction from him as he moves from one end to the other of a measured baseline. The nearer the peak, the more the surveyor has to turn his head to keep the peak in view as he walks along his line, and so the angle through which he turns his head gives us the distance of the peak. The longest baseline available to the earthbound astronomical surveyor is the Earth's orbit round the Sun, and we move from one side of it to the other every 6 months. Because of this, the nearer stars appear to be displaced a small but measurable amount from the position against the background of the more distant stars. But even the nearest stars are so far away that to measure their distance in this way is as difficult as measuring a distance of 25 miles from 2 points only 1 foot apart. Light, which, let me remind you, travels 186,000 miles in every second, reaches us in 8 minutes from the Sun, but it takes 4 years to get to us from the nearest star. Incidentally, this makes the light year a convenient unit of distance for astronomers. Because the Earth's orbit is comparatively small, the apparent displacements of stars more than 150 light-years away are too small to measure accurately, but fortunately we can use another method to find their distances. What we do is first to observe how bright the star appears to us on Earth. Then we work out how bright it really is, how bright it would seem if it were as close as the Sun. The difference gives us its distance. It's easy to see how bright a star looks but more complicated to find out how bright it really is. Luckily, the colours of stars are helpful here. There's a very useful relationship between the true brightness of a star and its colour. The hot blue stars are bright, and the cool red stars are faint, with a whole range of colours of known brightnesses in between. This range is called the main sequence, in which, for any particular colour, there is a known true brightness. Nearly all the stars we observe fall into the main sequence, with the exception of a few small, faint hot stars, the white dwarfs, and even fewer large, bright, cool stars, the red giants. Suppose we wish to measure the distance of a galactic star cluster. We measure the apparent brightness and colour of each star in the cluster, or a typical sample, if it's a rich cluster with more than about 100 stars. We find that the less massive stars in the cluster, which have not begun to evolve into red giants or white dwarfs, form a main sequence. So we know the true brightness of each star from its colour, we observe its apparent brightness on Earth, and from the difference between the two, we work out its distance. This method works as far out as a few hundred light-years. Then we run into difficulty with dust clouds in the space between the stars. These are 20 or 30 light-years across, and spaced about 150 light-years apart. They are concentrated towards the central plane of the galaxy, where we particularly want to look, and they interfere with our observations. They not only dim the light of the more distant stars, they also alter their colour, making them look redder than they should, by absorbing more blue light than red. So beyond 100 or 200 light-years, we have to, so to speak, allow for the dust in measuring brightness and colour. But further out still, the dust absorbs too much light for us to see the galactic clusters at all. Instead, we have to look for objects a little above or below the plane of the galaxy, where the dust is thinner. The globular clusters are suitable for this, because they are not so strongly concentrated to the Milky Way as the galactic clusters are. However, they show a very remarkable concentration along the Milky Way towards the constellation Sagittarius, and measurements of their distances from us show that they occupy a roughly spherical space, with its centre about 25,000 light-years from the Sun. This, then, is the distance of the centre of our galaxy. In the opposite direction, the stars thin out at about half this distance, so the radius of our galaxy is about 35,000 light-years, and its diameter about 70,000. Near the Sun, the thickness of the galactic disk is only 1,000 light-years, but at the centre it's about 15,000. Near the Sun, the stars are 5 to 10 light-years apart, but towards the centre they are much closer together, and we estimate there are 100,000 million stars in our galaxy. The Sun is a rather inconspicuous main sequence star, about 2/3 of the way from the centre to the edge. Herschel mistakenly thought the Sun was near the centre because he could not see far enough. The dust obscured his view. Because we are inside our own galaxy and surrounded by dust, we can't obtain a good view of it. However, there are other galaxies, and we can get an idea of what our own galaxy might look like from outside by studying them. They can be seen in all directions, except where the dust in our own galaxy gets in the way. Careful examination of the light from different parts of galaxies shows that they are rotating, and this has made them become flattened. Some galaxies are only slightly flattened by their rotation, while others are very much flattened, like ours. The appearance of any of these galaxies depends, of course, how it is presented to us, on edge, face on, or in some intermediate position. The most striking feature of some galaxies seen on edge is a dark central band, caused by their own dust clouds. Those seen face on show some spiral arms, which start near the centre and spiral a few times around before petering out near the edge. These arms contain dust clouds, and they are made conspicuous by the hot, bright stars recently formed by condensation from the dust. We can estimate the distances of the nearer galaxies from the apparent brightness of their brightest stars, and we find that our galaxy is larger than average, but not one of the largest. The great nebula in Andromeda is comparable, both in size and shape. These other galaxies tell us quite a lot about our own. By analogy with the others, we would expect ours to be rotating too. If it rotated as a solid wheel, it would be very difficult to measure the rotation, but in fact the inner parts rotate more quickly than the parts near the Sun, and the outer parts more slowly. From the measured distribution of the stars and dust in the galaxy, we can calculate that stars, say 3,000 light-years nearer the centre than the Sun, should travel about 10% faster than the Sun does. We find that they go 15 miles per second faster than the Sun. So we know the speed of the Sun is 10 times 15, that is about 150 miles per second, and in this way we find that the Sun takes about 200 million years to go once around the galaxy. Since we believe the galaxy is at least as old as the oldest stars in it, or 15,000 million years, the part of our galaxy containing the Sun must have rotated about 75 times. This tells us a bit more about the galaxy. It shows that it is a stable system of stars and that it will probably continue to exist in its present form for a very long time. It's much more difficult for optical astronomers to decide whether our galaxy has spiral arms, like some of the others, because even if there are any, they must lie one behind another, and the dust obscures our view. But observations with radio telescopes have helped our studies of the galaxy by penetrating those dust clouds.
The Milky Way was the third in the BBC series of talks, The ABC of the Universe. It was given by Dr Roderick Willstrop of the Cambridge Optical Observatory.